the variation of torque and slip with respect to the frequency as well as the supply voltage. Okay. So we did observe there that as the supply voltage changes and the supply voltage is square times the or the torque is proportional to square times the supply voltage. Therefore, uh, the variation in the supply voltage will affect square times the variation in the torque. Okay? That was one thing we had seen. And in the second case, we saw how the variation in the frequency will affect the performance of the machine. Okay? And in that case, we have seen with the variation in the frequency, the speed directly varies. Okay? If the frequency is increased, speed increases. If the frequency is decreased, speed decreases. Okay? And we have seen if the variation in the frequency occurs, then the similar performance of the machine can be obtained by varying the voltage. So by keeping the voltage to frequency ratio almost constant, we can obtain the same performance of the machine even with the variation in voltage and frequency. Okay? And we also have seen the relation between the full load torque and maximum torque, okay, and starting torque and maximum torque. So these relations and the things what we have seen will be used to understand the machine operation further clearly by solving some examples. Okay, so we'll take example. So a 230-volt 6 pole a 230-volt 6 pole 3 phase 50 hertz 3 phase 50 hertz 15 kilowatt induction motor drives a constant torque load drives a constant torque load at rated frequency at rated frequency, rated voltage and rated output. At 980 rpm. At 980 rpm and 93% efficiency. At 980 rpm and 93% efficiency. Calculate first point the new speed. Calculate the new speed if there is 10% drop in voltage and 5% drop in frequency. 10% drop in voltage and 5% drop in frequency. Second, the new output power. The new output power. The new output power with 10% drop in voltage and 5% drop in frequency. Okay? So that is what asked. Okay. So we'll go for solution. No. The first case voltage, let it be V1 is equals to 230 volt. V1 is not a primary voltage, V2 is not a secondary voltage. Okay, you don't think that. That is not the case here. So V1 is 230 volt. So V2 is 10% drop in voltage. In the sense, it will be 90% of V1. Okay, then F1 is equals to 50 hertz. Then F2 is 5% drop in frequency. That is 95%, 0.95 of F1. Okay. Then, so V2 will be is equals to 0.9 into 230. So this is 207 volts because 10% of 230 is 23. 230 minus 23 is 207 volts. Okay. Then frequency F2 is 0.95 of 50. So F2 is 5% of 50 hertz is 2.5 hertz. Okay. So 2.5 hertz, 50 minus 2.5 is 47.5 hertz. 7.5 hertz. Okay. So when the frequency is changed from 50 hertz to 47.5 hertz, synchronous speeds will also change. Okay. Therefore, NS1 is equals to 120 F1 upon P equals to 120 into 50 upon 6 is equals to 1000 RPM. Then NS2 is equals to 120 F2 upon P, number of poles are same. So this is 120 into 47.5 divided by 6 equals to. Is 950 RPM. That is 950 RPM. Therefore, as the synchronous speeds are different, slips will be different. Therefore, slips S1 is equals to NS1 minus N1. What is N1? So here N1 is 980 RPM divided by NS1 is 1000 minus 980 divided by 1000. So this is 2%. 0.02. Okay, or it is 2%. Okay. So here it is mentioned that at a constant torque load. Okay, so whether we are changing frequency or voltage or speed, the torque is remaining constant here. Okay, the torque is remaining constant. So therefore, for constant torque load, here torque is constant. Here torque is constant. Therefore, the product, the ratio, not product, the ratio S into V square by F for both the cases is same. Okay, S into V square by F for both the cases is same. Okay, so that is S1 V1 square by F1 is equals to S2 V2 square by F2. Okay. S1 V1 square by F1 is equals to S2 V2 square by F2. Okay. So here I know V1, I know F1, I know V2, I know F2. The only, and also I know S1. The only unknown is S2. Once I get the slip, I know the synchronous speed in the second case. I will be knowing the slip in the second case. I can find out speed in the second case. Okay. Therefore, S2 is equals to, I can write S1 V1 square by F1 into F2 by V2 square into F2 by V2 square. Now substitute all the values here. So S1 is 0.02 into V1 230 square by F1 50 into F2 is 47.5 divided by V2 is 207 square equals to, it is 0.023. Okay, or 2.3%. Okay. And therefore N2 is equals to NS2 to 1 minus S2. Okay. N2 is equals to NS2 into 1 minus S2 is equals to NS2 is 980, sorry, not 980, 950 into 1 minus 0.023. That is 928 RPM. The new speed is 928 RPM. Am I audible? Connection is intact, right?
Yes, sir.
Yeah. So the second case, here we have to find out the new power. Okay, new output power. Output power at F2 and V2. Okay. But if I would know what is the line current, line voltage, I would have find out in case of generator. But this is a motor, and I can't find out the output by just knowing the electrical values. Okay. So here I can write P out is equals to, we have one equation that we have seen in DC machines. That is P out is equals to 2 pi NT divided by 60. Now this T is what? Load torque. 2 pi N TSH by load torque. Now if I want the second case of P out, I can write P out 1 is equals to, okay, P out 1 is equals to 2 pi N1 into T1 divided by 60, and P out 2 is equals to 2 pi N2 into T2 divided by 60. So here Here 2 pi by 60 is a constant, and given that given that lower torques are constant, and given that T1 is equals to or T2 is equals to T1. Therefore, P out 1 is proportional to N1 and P out 2 is proportional to N2 because all other things are remaining constant. Taking ratio, I can write P out 2 by P out 1 is equals to N2 by N1. Okay, or P out 2 is equals to, it is 15K multiplied by 928 divided by 980. It is 14.204 kilowatt. So new power output is 14.2 kilowatt. Okay. So this is the solution of the given problem. Okay. Then we will move to next one. Example, a three-phase 400 bar 200 volt star connected wound rotor induction motor, wound rotor induction motor has 0.05 ohm per phase rotor resistance and 0.32 ohm per phase standstill rotor reactance. Find the additional resistance required in rotor required in rotor circuit to make standstill torque torque equal to make standstill torque equal to maximum torque. To make standstill torque equals to maximum torque. So here the given things are F is equals to 50 hertz. Oh, it is not mentioned, right? Not mentioned. Okay, so V1 is or V is 400 volts and E2 is 200 ohms. R2 is 0.05 ohms and X2 is 0.32 ohms per phase. When I write R2 and X2, they are per phase only by default. Okay. Then what should be the R external? R external is equals to what? When standstill torque is nothing but starting torque. TST is equals to Tmax. TST is equals to Tmax. That is what it is asked. Okay. Now we have the relationship between Tmax and starting torque. Okay. Starting torque and maximum torque. We have TST by Tmax equal to 2a by a square plus 1. So we have the relation TST by Tmax is equals to 2a by a square plus 1. You remember only one equation. You can write both the equations. Okay. It is 2asf by a square plus sf square. Full load torque by maximum torque. Okay. Full load torque by maximum torque is 2as by a square plus sf square. Now if it is starting torque, put s equal to 1. It is 2a by a square plus 1. If you remember one equation, you can write both the equations because slip is 1 at starting. Okay. Here TST is equals to Tmax. Therefore, 2a by a square plus 1 is equals to 1. TST by Tmax is 1. Or I can write a square minus 2a plus 1 is equals to 0. Cross multiplying. Okay. Solve this. What is a square minus 2a plus 1?
A minus 1 whole square.
It is a minus 1 whole square. Okay. This is a minus 1 whole square equals to 0 or a minus 1 equals to 0 or a equals to 1. This is important for me. A equals to 1. Okay. Now, what is A?
R2 by X2.
It is not only R2 by X2 now. There is some external resistance added in the rotor circuit. Now I want the starting torque to make equal to maximum torque. What is the condition for maximum torque? R2 should be equal to S into X2, right?
Yes, sir.
For maximum torque, okay, at starting, for maximum torque at start, rotor resistance, I will write in statement, is equals to standstill reactance. Is it right? R2 should be equal to X2. Now, what is the rotor resistance? The rotor resistance is to make the starting torque equal to maximum torque is implicit rotor resistance of 0.05 ohms plus external resistance. Okay. So as external resistance is added in rotor, my R2 plus R external is now equal to X2. Okay, R2 plus R external is now equals to X2. Okay. Now what is external resistance? R external equals to X2 minus R2. That is 0.32 minus 0.05. So this is 0.27 ohms. Right? 0.32 minus 0.05 is 0.27 ohms. So if I add 0.27 ohms in the rotor circuit, if I add 0.27 ohms in the rotor circuit during starting point, then my starting torque will become equal to maximum torque. That is the meaning. Okay. Is it clear?
Yes, sir.
Next. Go to next example. A three-phase 50 Hertz 8-pole induction motor has full load slip of 2%. The rotor resistance and standstill rotor reactance per phase, I will write R2 is equals to directly the rotor resistance standstill reactance per phase, R2 is equals to 0.002 and X2 is equals to 0.007 ohms. Okay. Find the maximum torque in terms of full load torque and speed at which maximum torque occurs. And speed at which maximum torque occurs. Okay. So solution. So I can write here F is equals to 50, P is equals to 8, SF is equals to 2%, that is 0.02, R2 is 0.002 ohms, X2 is 0.007 ohms. Okay, then what I want to find is maximum torque in terms of full load torque and speed at which maximum torque occurs. Okay. You can find slip at maximum torque. Okay. Slip at maximum torque, that is SM is equals to A is equals to R2 by X2. So R2 is 0.002 x2 is 0.007. So this I can write it as. So it is 0.285. Okay, or 28.5%. The slip at maximum torque is 28.5%. Okay, then I can write speed at maximum torque. Speed at maximum torque. N max is equals to Ns, okay, or Nsm into 1 minus Sm. So this implies Nsm, the synchronous speed. Okay, synchronous speed is same, it won't change. Ns synchronous speed is 120 F upon P. So it is 120 into 8 divided by, sorry, 120 into 50 divided by 8. So this is 750 RPM. Okay. So N max is equals to 750 into 1 minus 0.285. So this is 535.7 RPM. 536 RPM I will take. Okay. Now this is the new speed, the speed at which maximum torque occurs. Next I have to find out the relationship between maximum torque and full load torque. Okay. So we have full load torque to maximum torque as 2a SF divided by a square plus SF. Is it? Or SF square we have. A square plus SF square. So I have the value of A. I have the value of SF. Okay. So the full load slip is 2%. Okay. The full load slip is 2%. Okay. So I can write this as if you want to take the reciprocal T max divided by Tf, because I want the maximum torque in terms of full load torque equals to a square plus SF divided by 2a SF equals to A is 0.285 square plus SF square is 0.02 square divided by 2 into 0.285 into 0.02. So T max is equals to 7.16 TF. Okay. So the maximum torque is 7 times the full load torque. Okay. Maximum torque is 7 times the full load torque. Okay. So this is what was asked in this statement. So these are few examples on the relationships between torque, slip, and the voltages. Okay. So next we'll look again into torque speed curve, and here what we want to look is what are the limiting values of the torques. Okay. Torque speed curve. Now already we know what is the nature of torque speed or torque slip curve. Okay. So when I draw the torque speed curve, okay, so this is a torque, this is speed, percentage speed, okay, percentage speed of ns. So you can observe in the torque slip characteristics, the speed is varying from left to right, whereas slip is varying from right to left. Speed is varying here from left to right, slip is varying from right to left. Okay. So here I am considering the speed. Oh, when the speed is 0% and the speed is say 20%, and the speed is say 40%, and the speed is say 60%, and the speed is 80%, and when the speed is 100%. Okay. And I have T max. Okay, so this is a T max, the maximum torque. Now, when the torque varies with respect to the speed or with respect to the slip, it will be initially varying linearly, and it is reaching the maximum value. Okay. And it is dripping somewhat and it is raising again. Okay. So this is the torque speed characteristic. Okay. So here the Tmax is, okay, the Tmax value is, it is 2.5 times Tf, that is full load torque. T point 2.5 times the full load torque. Okay. So here let this be the speed. So here it is ns. When the rotor speed is equal to ns, the torque developed is 0 because the rotor stops. And this is the speed n. So the torque corresponding to this speed n. Okay, let me take this as the full load torque. Tf. Okay, let me take this as full load torque Tf. Okay, and this torque let it be 1.5 times Tf. Okay, 1.5 times Tf. So we know this torque is a full load torque. Okay, and this torque is breakdown torque or pull out torque or maximum torque. Okay, this torque, the dip minimum torque, okay, is called pull up torque. It's called pull up torque. Okay. and this torque is known as locked rotor torque. Okay. So what happens if the pull-up torque, if the rotor torque, if the rotor's speed is below the pull-up torque value, the motor tries to stop. Okay, the speed is decreasing after the maximum torque condition. The speed continuously decreases. When the motor reaches the pull-up torque, the motor stops. And it will again start developing the starting torque. Locked rotor torque is nothing but my starting torque or standstill torque. So here the starting torque is 1.5 times the full load torque and the maximum torque is 2.5 times the full load torque. Okay. Hence it is called pull-up torque. Okay. Either the motor will pull up to starting mechanism again if the stator retains its supply, okay, or before this torque occurs, the motor is pulled up into operation. That is called pull-up torque. So never the motor should be operated beyond pull-up torque. But what will happen in the practice is, okay, there will be a automatic motor control mechanism which is decided by the torque slip value of the motor. If slip value of the motor falls below certain level, then before the pull-up torque is reached by the motor stops. How the motor stops? They will disconnect the stator with the supply. The switch will be opened. The MCB operates or the relay operates and the motor supply is isolated or disconnected. Why this is so? Because if the motor tries to run at a very low speeds, then the load associated or load connected on the motor shaft will malfunction. And in certain critical load conditions or in certain critical loads, we don't expect that the loads should operate undesirably. So therefore, when the slip of the motor falls below certain value, they will be taking out the motor supply and they will be and the motor will be disconnected from the supply terminals and motor stops operating. Okay, and motor stops operating. Okay, so this is one point. That is, when the motor slip is below certain level, automatically there will be an arrangement made to stop. If there is no automatic arrangement made to stop the motor, then when the motor torque increases beyond maximum torque, when the motor slip increases beyond maximum torque condition and it reaches pull-up torque, it will automatically stop. Okay, so there are three conditions when the motor will stop. You should remember one thing. There are three conditions when the motor will stop. One, when the motor attains the synchronous speed. When motor attains the synchronous speed. Second, when the motor torque is beyond the pull-up torque. When motor torque is beyond the pull-up torque. Third, external mechanism used to stop the motor if the motor slip rises above certain value, not falls. Slip rise means speed falls. If the motor slip rises above certain level. Okay. Similarly, at one more condition, the motor will be stopped if the maximum torque of the motor goes beyond 2.5 times the full load torque, the motor stops. If maximum torque produced is beyond 2.5 times the motor full load torque, the motor is made to stop. Because at those large torques, the mechanical breakdown of the motor and the load can happen. To avoid the mechanical breakdown of the motor and the load, the torque development is controlled just to 2.5 times the full load value. Okay, so this curve gives that information when the motor is operated at stable operation. See, this is a stable operation until the motor reaches, okay, until the motor reaches or until the motor operates in the linear region of the curve, the motor is stably operated. So when the stable operation of the motor is expected, the slip we generally keep less than 10%. Okay, so here as per the curve, the maximum torque is occurring at 80% of the speed, that is 20% of the slip. Okay, but when I want to operate the machine in a stable mode, then I generally keep the slip less than 10 to 15%. Or I can say I will keep the slip below the slip that causes maximum torque. Okay, so I hope this is clear. Any doubts? Yes?
No, sir.
So with this, I will end the today's session. Okay. In the next class, in tomorrow's class, we will see the overall characteristic of the induction motor, the complete characteristic of the induction motor, that how the induction motor behaves as a motor, how it behaves as a brake,